in the last decade or so, a plethora of devices which are interconnected have emerged under this ecosystem of Internet of Things. So what exactly is Internet of Things? So nowadays, there are some consumer devices like smartphones, wearables, like smart glasses and all those things. And also there are some devices which are actually in your household, like your Google Home or Alexa Home. And all these devices are actually connected to the internet. And there are also some wireless sensor nodes which are placed in the industry for security, for automobiles and all those things. So all these devices kind of are interconnected to each other and also connected to the internet. And each of these devices form a part of the cyber physical system. So all these devices connected to the internet are known as cyber physical systems. And since they are connected to the internet, they are also connected to each other in some way. So recently, this kind of a ecosystem has emerged, which is known as Internet of Things. And if you look at few of the quick facts about IoT, you will realize that more than 25 billion devices have already been connected by 2020. And it's a market which is pretty huge. It's like a 7.1 trillion market. So if you look at India's GDP, it's only $2.6 trillion. And if you look at this IoT system, it's like $7.1 trillion. So it's huge market as compared to even our GDP. Also, one more thing that these interconnected devices have led to is a huge amount of data transmission. So all of these data kind of send some data to the cloud or the internet. So because of these devices sending data across each other or sending data to the internet, you have like a traffic of 44 zettabytes of data. If you convert this in terms of GB, it's like 44 trillion GBs of data that is being communicated. And because of this, there's a huge data explosion, as they call it. And this is also known as the big data. So you have asynchronous data. I mean, these data are not synchronized with clock, because whatever messages you send are real time and they're not actually synchronized with clock. So all these data are basically sent throughout the world. And it has led to a huge data explosion. And this is basically known as big data. So big data is nothing but a name given to this asynchronous flow of data that is going on throughout the internet and all. So the main sources of these data are healthcare sector, travel sector, education, telecom, e-commerce, media entertainment, retail, and finance. One of the major sources which they have actually missed here is social media. So social media leads to a large amount of, it leads to production of a large amount of data. So, okay. So also there's one more important point which is related to artificial intelligence. So we are now living in an era of artificial intelligence revolution. AI has got multiple applications and these applications have been rising rapidly. So earlier there was no AI application in your mobile phones, but nowadays all of you must be using your voice assistants like Alexa, OK Google and all those things. And also camera filters like Snapchat, or there was also a Face app which came recently. So these are some of the progresses of the recent developments which have propelled the development of these memory devices as well as these CMOS computing systems. So this big data especially, there's a huge amount of data that is flowing across this universe at the present time, and you need some memory devices to store them. What we don't see is that it's the cloud which is actually storing these data. I mean, your WhatsApp chats and all, where are they stored? It's actually a cloud which is storing them. So, it's a very, I would say, interconnected world now, and there's a huge amount of data that is flowing. And in order to mitigate or in order to cope up with this huge data explosion, you need large amount of memories. Okay, so with that, I would also like to tell you that there is also a shift in the application of the servers. I mean, for a long time, these clouds or these servers have been able to host this data. But recently, there also has been a shift in the application for which these servers were used for. So initially, or I would say till 1980s or 1990s, or maybe even early 2000s, these servers were mostly compute-centric. That is, they were basically used for solving some equations like differential equations, and the bottleneck was basically CPU speed or the memory speed. That was the bottleneck there. However, nowadays, with huge amount of data that has come, the computing focus has now shifted to data-centric paradigm. So what is basically data-centric paradigm is now these servers are being used for analyzing these petabytes of data. So, Amazon server, this Google server, these are basically now used just for data analysis. And, there have been like a significant rise in the number of courses that people are offering on data. For instance, the courses on like MBA courses on data mining, MBA courses for data analysts and all. So there has been a rapid increase in all those courses and all those jobs across the world, I would say. But here, if you look at this table, you'll see that the bottleneck for the compute-centric paradigm is the CPU speed or the memory speed, while the bottleneck for this data-centric paradigm is the storage. So normally what we'll see, or normally what we'll think is that memory and storage are basically the same things, but they are not. So we'll study later why they are not the same thing. So with that, I would go ahead and tell you about the memory organization. So I don't know how many of you have actually opened your laptop or CPUs. I'm not talking about opening them by power on, but by opening them by unlocking those screws and all. So if you open your CPU or your laptops, what you'll find is something like this. So you'll have three different areas which I have identified here. So you'll have something like this where your registers and SRAMs are placed. Then you have these two slots for RAM, which is nothing but the DRAM. And you have this hard disk over here. So these are the locations where your memory is in your laptop or in your CPUs. Now the way memory is organized in a computing system is something like this. So you have this different cores of CPU. So nowadays people work with multi-core CPUs. There are 4 cores, 8 cores, 16 cores and so on. So each of these cores have got dedicated registers. So the smallest block of memory that is available in a computer system is this register. So this register is basically very fast. So you can get the data from the register in just one CPU cycle. So its speed is very fast, close to 0.1 nanosecond. However, its size, as in the physical size, is very large. I'll come to that later, but its physical size is very large. And that is why you can accommodate only few of them in this core. So in terms of its memory size, it's very low. It's of the order of some 100 bytes. The next hierarchy in the memory that is available immediately adjacent to the core is the cache memory. There are basically several levels of cache, but what exactly is a cache memory? So cache memory is nothing but arrangement of a content addressable memory, which is a CAM, and a SRAM. So I'll discuss about these later, but as of now, I'll just let you know how exactly a cache works. So whenever your program wants a data from the memory, so all of your data is basically stored in some memory, which is actually called the main memory or the DRAM here. Now, whenever your program wants to access any data from the memory, it basically has to communicate very far from the chip. So what it does, it basically goes to this main memory, fetches the data and brings it back and saves it to this SRAM array. So how exactly that happens is, whenever your program has to access any memory location from the main memory, it basically goes to the main memory, fetches that data, it stores the address of that memory location in this CAM array over here. So the address is stored over here, and the data that was fetched from here is stored in the SRAM array. So corresponding to each of these address of the main memory, you have some data, and the same copies are made in this CAM array. So in CAM, you have the address, and your SRAM, you have the content. So now, suppose that program again has to fetch the same memory location. So instead of going to this memory location, what it does is, it just searches for this data in the CAM or in your cache. So if it gets an address that, okay, I want to fetch data from this location, it will simply put this address over here as a query. Now, what does a CAM do is, it just tells you whether this address is present in this array or not. So you present it with any address. If this address has already been accessed and stored in this CAM, it will simply tell you that, okay, this address is already in the CAM, and it will denote it by this hit. So if you provide it with any query address, this CAM will search for this address throughout it. And if that address is available, it will say that, okay, it's a hit and we have this address available. And then instead of going to the memory location, it will simply fetch this content from the SRAM array. So instead of having communication with a memory which is off chip, or which I would say is far away, it simply fetches that data from a memory which is very close to it. So the speed is very high, and that is why you have different caches. And cache, as you may know, that as the computers are becoming more and more fast, the cache size is basically increasing. And it's the cache which is kind of the, after register, it is the fastest kind of memory. And the cost of your computers actually depends on the size of the cache memory that you have. And similarly, the power dissipation of your computer also depends on the cache size. I'll discuss that point later. Levels of cache. So L1 cache is the fastest of all the caches, and it is very close to the core, as you can see here. Then there is this another level, which is called L2 cache, which is somewhat slower than the L1 cache, but its size is larger, and it is placed far from the processing core. Then there is another level of cache, which is called the L3 cache, which is not basically having the same structure as this. So this L3 cache is actually made up of embedded DRAM. So I'll discuss about embedded DRAM later, but this is also fast memory, but its size is larger as compared to your previous two cache memories. So it depends on how far your cache is from the processor. If it is very close to the processor, its speed will be very high, but its size would be small. If it is somewhat far from the processor, its speed would be somewhat less, but its size would be large. If it is very far from the processor, like L3 cache, what will happen is its speed would be further low, but its memory size would be large. So it's something like that. Things which are close to the processor need to be very fast, but since they're very close to the processor, their size would be small, their memory size would be small. Their physical size would be large, but their memory size would be small. So there's a difference between the physical size and the memory size. So the physical size is the size which one memory cell occupies on your chip, whereas the memory size is how many such cells are actually placed. So you understand this point? So then this entire thing, I mean, starting from this core to registers, then L1 level of cache, L2 level of cache, and L3 level of cache, these are all present on your motherboard. So it's kind of your embedded or on-chip memory. It is called on-chip memory just because everything is kind of in one chip. However, this DRAM is actually another component. You see, it's another component. There are two ports basically here for two RAMs. So it's another component in a computing system. So main memory or DRAM is basically something which is, it's slow. So fetching a data from a DRAM takes at least more than 100 cycles. However, its size is large and its size is in some gigabytes. So the size of main memory is in some gigabytes. The size of these caches, like for instance, this L1 cache is in some kilobytes. The size of L2 cache and L3 cache is in some megabytes. However, the size of this main memory or RAM is in some gigabytes. For instance, you have like 16 GB of RAM or 8 GBs of RAM nowadays in your computing systems. So this is basically main memory, which is the DRAM. You must have also seen different types of DRAM, like your system may have SDRAMs or it may have DDR3 RAM or DDR4 RAM. So they are all different variants of DRAM, but inherently they are DRAMs. So the next level of hierarchy is this hard disk, which you have, and the size of the hard disk is like in some terabytes. However, its speed is pretty slow. And if you want to access any data from the hard disk, it takes around 10 power 6 to 10 power 8 cycles. And then the next level of storage is the tertiary storage, such as magnetic tape or disk or RAID, which is available in your, I would say, servers. So it's the slowest form of memory, but it's the most dense memory, or its size is in some petabytes. So it's like the organization is such that the closer you are to the core or the processing unit, the faster your memory element is. However, its memory size is less. The far you start walking away from this core, the memories will become larger in size. However, their access speed will become very small. Is it clear till now? Which is kind of the difference between memory and storage that I was pointing out before. So if you look at the systems of 1980s, and if you compare the access time of different memory elements. So as I discussed, there are two kinds of memories. One is on-chip memory and off-chip memory. So on-chip memory is something which is kind of there with your CPU, and off-chip memory is something which is apart farther from the CPU. And there's this online storage and offline storage. So online storage basically means memories such as hard disks, which are actually storing things when your computer is running. And then there is this offline storage, which actually copies this data from the hard disk. And the data here in the offline storage has to remain for a large period of time. So if you look at the cost basically reduces as you go from on-chip memory to off-chip memory. However, the speed also reduces if you go from on-chip memories to off-chip memories. So for instance, your CPU registers and all, their access speed is close to some nanoseconds. However, for getting a data from L2 cache, it's like the time that you need is less than 5 nanoseconds. So your frequency of a processor is close to 4 gigahertz, right? So with registers, you can actually work very close to that frequency. When you have to get data from this L2 cache, you require somewhat large time. Now getting data from DRAM is basically even, I would say, a slower process. It takes around 60 nanoseconds of time.
Yeah.
Now, if you want to read or write the hard disk,
So
it's like 10 per 7. It takes around, who is it? Anyways. So it takes around 10 per 7 times the clock frequency, or I would say it takes around 5 milliseconds to read or write a data to the hard disk. So if you see in terms of access time, there's a huge gap between the DRAM or the main memory and your hard disk. So what people did was, just to make sure that these two are different categories of data storage or data, I would say, retention, they kind of called this portion over here as the memory and this portion as the storage. So that is how they differentiated between the data, between the memory and the storage. Now, if you look at the computers today, the gap has actually reduced because of the presence of this SSDs. So there are these solid state drives which are present in your laptops or in your computers. So they are actually faster than your hard disk, but still they are slower than your DRAM. So now we earlier called this as memory and we call this as storage. Now another memory element or another player has come, which we call as SSD, which is kind of having a faster access time as compared to this disk, but is still very slow as compared to the DRAM. So there is still this gap, and people call this gap as the memory and storage gap. Now in the future, what people are predicting is that there would be this storage class memory, or basically there would be this SCM or storage class memory, as the IBM people call it, which would actually fill this gap. So there would be a new memory which would be in between this, or whose latency would be in between this. So what would be the properties of this SCM? First of all, its access speed should be higher than SSD, but lower than DRAM. Second, its cost should be lower than this DRAM, but higher than flash. So these are the two properties that these storage class memory should follow. And why is it called storage class memory? Because memories are considered to be fast speed, but lower in density. However, these storage elements are considered to be very slow in speed, but very fast, or I would say very dense. I would say their capacity, memory capacity, has to be large. So for these SCMs, what should be there? That it should be fast as memory, but its density should also be high, close to the storage elements or close to this storage class. So this SCM is something which all the emerging non-volatile memories are targeting. So they're not trying to replace this DRAM, they're not trying to replace this hard disk, they're not trying to replace this disk. What they're trying to fill in is this gap between your memory and storage, and in the form of this storage class memory. And into segregation of memory devices, and how we basically categorize different memory devices. First category is based on whether your data is retained once the power is switched off. So based on that, we have two different classes of memory. One is called volatile memory and one is called non-volatile memory. So for volatile memory, the data is lost once the power is turned off or once you turn off the supply. While for the non-volatile memory, the data is retained even after the power is shut off. Now, even in volatile memory, you have different classes. For example, you have this static random access memory, you have this dynamic random access memory. So there are these two words, one is static and one is dynamic. What do you mean by static? So in static memories are basically those memories where the data is stored for a long time, or where you don't want to fetch the data for a long time. And what I mean by a long time is close to some milliseconds. So for a processor, a millisecond is also a very long time. So that is, whenever I'll call long time, that means millisecond in terms of a processor speed. Now, static kind of RAMs, what they develop on, or what their operating principle is, that they are kind of storing the data as stable states of a bistable vibrator. Now, the second class of this volatile memory is the dynamic memory, where the data is stored as a charge on the capacitor. So this charge is usually a parasitic. This charge is usually stored on a capacitor, which is usually parasitic. What I mean by parasitic capacitor is, at the input of each of the MOSFET, you have this gate capacitance. And then you have this gate to source capacitance, gate to drain capacitance, which are kind of, gate to drain capacitance is kind of a parasitic capacitance. So, it's stored basically on those parasitic capacitances and not dedicated capacitances. I mean, you can also like include a dedicated capacitance and store the charge on that, which is usually done on the DRAM. But you can also have architectures where the data is stored as charge on a capacitor, which is parasitic. Since your data is being stored on a capacitor, and the capacitor usually leaks charges whenever it is connected to any transistor or something. So it needs continuous clocking or continuous refresh cycles. However, since it's only storing charge on a capacitor, so storing charge, let's say it represents bit 1, and when charge is not there, it represents a bit 0. So that way, it's a very simple kind of memory. So in terms of the static kind of, static memories, you also have this registers, which I showed that it was kind of the first class of these memories. So the registers are kind of the fastest memories, but in terms of area, they require the largest area. Or in terms of the physical memory size, they are the largest, which is the register. And as I told, so to store 1 bit of data, you need at least 22 transistors over here. Now let us look at the different forms of memory, such as SRAM and DRAM and all those things. So here we have SRAM, where the data is stored basically as a bistable, I would say as a bistable element. So it consists of like 6 transistors, 1, 2, 3, 4, 5, and 6. So to store 1 bit of data, here you need 6 transistors only. So the physical area would be definitely smaller than a register. However, this is the fastest kind of memory. This is somewhat slower as compared to register, still the fast memory. But the problem with SRAM is that since it's a digital circuit, and with CMOS scaling and all, its leakage power is very high. And also the area that it consumes is very high. So you cannot have a very large array of SRAM and have a very small processor. So at the end of the day, what you want is your processor should be very small in size, small in area. You want handheld devices. So your processor area should be very small. And in that small processor, you need to have a very large memory as well. If your memory is something like this, which occupies 6 transistors for storing 1 bit, you cannot have a very large memory because you also have to think about the area. So there's always this trade-off. And in SRAM, there's one more trade-off, which is also known as write and read conflict, which I'll discuss when I'll be taking lectures on this SRAM. The next class of memory is called the DRAM, where you have a transistor like this. So it's an NPN, NMOS, where your bit line is kind of a drain. And at the source, you have this capacitor, which is connected to it. So here, how the data is stored is, the data is stored in terms of charging and discharging of this capacitor, which can be controlled with the help of this MOSFET. However, the problem with DRAM is that it needs continuous refreshing. Because even when the transistor is off, there is something which is known as subthreshold current or the leakage current which flows through it, and it will kind of drain the charges that are there in this capacitor. So it needs to be refreshed every 1 millisecond. So the refresh cycle is kind of every 0.1 milliseconds or something. So every 0.1 milliseconds, you have to again refresh the charge so that it is stuck to the, it is showing you the correct value. So these are the 2 volatile memories. Now let us go to the non-volatile memories. So in non-volatile memories, the first class of non-volatile memory is based on charge trap. One of them is flash and one of them is Sonos. Okay, so it's all these. So flash memory is also nothing but a MOSFET in which you have an additional floating gate or an additional storage layer. So there is this control gate, which is similar to the gate in a MOSFET. The body is similar to that in the MOSFET, but you have an additional floating gate. So how exactly it works is you apply a very high voltage to this control gate. It kind of extracts some amount of charge in this floating gate. Now the charge in the oxide layer shifts your threshold voltage, and as such, the threshold voltage basically leads to different memory states. So in your flash memory, if this charge is stored in your floating gate, then it's called a floating gate flash. And if this charge is stored in some storage layer, which is like a silicon nitride, it is called a Sonos flash. So the problem with flash is the endurance is very low. I mean, since the charges are being tunneled from this channel to this floating gate or through or this storage layer, so this oxide gets the quality of this oxide degrades over time, and it becomes non-usable after like 10 power 5 cycles, or after 10 power 5 kind of movement of the electrons between this substrate and this charge trap layer or the floating gate. So next in our list is this polarization change memory, which is kind of FRAM. So the ferroelectric RAM also works on a similar principle. Instead of this floating gate, you have a ferroelectric layer here, ferroelectric layer. So the ferroelectric materials have this special property that they are non-centrosymmetric, and as such, they have this inherent polarization, and polarization can be thought of as charge. So you apply some gate pulse to this, the charge can be the charge can be different from, like, the charge can be actually moved from positive charge to negative charge, and as such you can have different threshold voltages, and those two different threshold voltages correspond to different memory states. So the next level of memories is based on resistance change, and in that first is kind of the magnetic RAM. So a magnetic RAM basically dwells upon the spin in the magnets. So every electron, with every electron you have an associated spin. So how an electron has a spin? So an electron moves around the nucleus. So it can be thought of as a current moving around in a circular path. So if you remember your 12th standard physics, so whenever a current is there, which is going in a circular path, you curl your fingers around that, and the direction of the thumb will give you the magnetic field. So spin is basically, it can be related to the kind of impact of magnetic field on electrons. So that is kind of characterized by this spin. So how exactly a MRAM works is, you have a pinned magnet where the spin is along one direction, and you have a soft magnet over here. So by moving a current from the pinned magnetic layer through this tunnel barrier to the soft magnetic layer, you can actually change the direction of the spin in the soft magnet. So if the direction of spin in the soft magnet and the pinned magnet are same, along the same direction, its resistance is low. If the direction is opposite, that is, it is anti-parallel, then the resistance is high. This phenomena is known as TMR, or tunnel magnetic resistance ratio. So the problem with this MRAM is that this TMR is really small. I mean, the ratio between, or I would say, the ratio between the resistance of the anti-parallel state to the parallel state is just 3 or 2. So a maximum tunneling magnetic ratio of 800% has been reported so far. So R on by R off for this kind of, or I would say the memory window for this kind of memory is very small. Anyways, so let us look at the next, I would say, resistance change memory, which is this phase change memory. So this PCM or PRAM, whatever you call it, consists of a phase change material in between your electrodes. And you know, there is this protrusion of an electrode, which is actually a heater. So you have a heater inside this phase change memory. How it heats the phase change material is, whenever you pass a current through this, whenever you pass a current, you have this Joule heating. So just by passing a large amount of current, you heat this phase change material. And if you cool it down rapidly, it gets to amorphous state. And if you cool it down, giving it some time to stabilize, it cools to the crystalline state. So the resistance between the amorphous and the crystalline states are different. And because of that, you have different resistance states, which correspond to different memory states. That is how your PCM works. But the problem with this is, since you have to heat the phase change material, so you need a very large amount of current. So the power consumption of PCM is really high. Then let us look at this RAM device, where an insulator is basically sandwiched between two electrodes. So this is basically a MIM structure. Now, once you induce some vacancies or some defects in this oxide, these two electrodes can be connected via these defects. So the formation of these conductive filament, or once these filaments or oxygen vacancies are induced in this insulator, you can actually reversibly disrupt it, or you can actually form it. So it's like, initially your MIM capacitor is there, the insulator is defect free. What you do is you stress it with a very high voltage. Once you stress it, you achieve soft breakdown. So once the soft breakdown is achieved, you have these oxygen vacancies in the insulator layer, which actually connect your top electrode to bottom electrode. Once the top electrode and bottom electrode are connected, the resistance is low. Now, just by applying a very high voltage, a very high negative voltage, you can actually attract some of these vacancies towards this electrode. And as such, you will uncover some layer of insulator. So whenever there is an insulator in series with something, the resistance goes high. So just by applying few pulses, you can actually change the state of this RAM from low to high or high to low. Now the next class is this conducting bridge RAM. So in this conducting bridge RAM, you have basically these metal atoms. So it's basically based on reactions. So what happens is, in this solid state electrolyte, you do not have an insulator. Instead, you have a solid state electrolyte. So in solid state electrolyte, at this interface, there is a redox reaction taking place. And because of this, some metal atoms, or I would say metal ions, they get inside the solid electrolyte, and they may connect this bottom electrode to the top electrode. And now if you apply some negative voltage here, these positive metal ions will be attracted back to this top electrode. And then again, some amount of this solid electrode will be exposed. Since this solid electrolyte is kind of an insulator, so it will offer you higher resistance. So these are resistance-based memories. So they are commonly known as RRAMs. I mean, this is known as OXRAM in general, but you can also call it RRAM. So in general, these all memories are known as RRAMs. This is a flash memory, which is a different class of memory. So all these memories are now in a nascent stage. I would say they're not technologically very mature, but this flash is very mature.